Square root of x, all right. And hopefully that's what I have in the notes. I have no idea. It doesn't look familiar to me at all. But I do remember the square root of x, so that's it. So you could, basically, and you could integrate this and get j star. J star is x to 3 halves. I'll let you do the integration, or look at the notes, all right? So we had an upper bound that was quadratic. That was wrong. It's actually x to the 3 halves, just from integrating this expression. I'm too lazy to integrate. All right, so we solved this problem, all right? And then what do you do? So yes?
So x is the initial condition?
Well, here it's not.
Okay,
so here it is. So the definition of this, x here equals x, right?
Yeah.
And so you say, well, this is just a function of x. So the same kind of thing you do with Markov chains, where you start off with something that has a very precise meaning. I start at some given position, and I go along, and I optimally transverse to the end. To hear this, a lot of physics and intuition, but then you say, forget that, it's a function of x, and it satisfies a fixed point equation. And it has no meaning. So here it has no meaning.
So if you were to implement u star, it would be x and t that you would measure?
Oh, yeah, that's a good point. So u star of t equals phi fluid star of little x star of t, which is alpha plus the square root x star t over r. Exactly. Yeah.
And x star of t is the result of
yeah.
applying.
Yeah, it's pure state feedback, and that's it. Yeah, and it's really appealing. You remember the cost? Let's write down again. The cost is x plus u squared, basically, right? So by having the policy be the square root of x, you're balancing the costs, right? So you've got x here, and then u squared is just x as well. So you basically, there's a balance that's being created. And as you make r get larger and larger, u gets smaller and smaller. So you turn off the control. All right, cool. So I can't prove anything, but it's done. So in this example, it's so amazing. So you'll just have to look at the notes. Now, so this is not feasible. Feasible for the MDP. But you can go through and just fix it. Let's just call it phi of x is the minimum of x and this fluid guy. It's a star. So let's fix it. Let's take this thing we got from the fluid model, which we justified through Taylor series last time, and take a min of x in this so that we make sure it's feasible. Because remember and then if you go through, can you all see this? See, if you actually solve it using, we're going to learn about value iteration as we go along, but we actually talked about it briefly. You can barely see the difference between the fluid and stochastic solutions. They're just, basically, for r equals 1/2, and here's x. Both policies are just linear. They're just x up to some threshold, and for the optimal policy, the threshold is about 2. And for the fluid policy, it goes all the way up to 3. Right? And they diverge. You know, the fluid policy looks like that. And the stochastic policy does that. They're identical. There's a gap of that much in terms of the policy. It's amazing. It's amazing in this case. And it's because of the fact that our hypothesis that the value function was smooth was really true. You know, if you do a second order Taylor series expansion of this, you know, for x bigger than 1, it's just going to 0. All right? So it's basically, when we were fooling around last time with Taylor series, all of our assumptions were very much justified. So the Bellman error is bounded, and you know, better than that. So so this is a great example where this works almost perfectly. Yeah.
Could you explain why is it not feasible for the MPP?
Oh, well, let me remind you. Yeah, this one's dead. Let's go to the trash, excuse me. Yeah, it's just the fact that, you know, there's a positive probability nobody arrives, you know. And so if nobody arrives and ut is bigger than xt, we'd make the buffer go negative. What does that mean? So we had a constraint there that ut is always going to equal to xt. I mean, less than equal to. All right, so I'm not saying this always works, okay? I'm just saying that, I'm saying that the basic philosophy of control often works, that you take a really naive, stupid model that captures the essential property of the system to be controlled, and you've done 99% of the work. So worrying all about this Markov chain, should we model AT as Poisson or Cauchy or blah, 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 in the end it doesn't matter. You know, you're going to get, you know, maybe if we made AT more heavy-tailed, you know, maybe it didn't have a third moment. If it didn't have a second moment, I'd see a gap, I think. But if it had a, maybe not. Actually, it'd be fun to find out. I don't find it didn't occur to me, but you'd see a bigger gap with a heavier tailed A. But you'll capture the policy almost perfectly. You know, and so one of my motivations to teach stochastic control is to tell you most of the time, don't bother. Stochastic control gives you means to explain why you shouldn't bother. You know, you can get away with your stupid fluid model and 99% solve the problem. Basically, when you're done, you've got a policy with 1 degree of freedom, and now you can just optimize it using Monte Carlo. Take data from the real system and find the optimal R that makes you happiest. You know, it gives you a family of policies. It's beautiful. I should say this one. You know, yeah.
There's no reason for that policy to be integers, right?
Oh yeah, that's. I mean, yeah. Actually, this is done with integers. Even with the integer constraints, you can't see the difference. It's amazing. Yeah. So we did a floor or something. I don't know. But yeah. So in your notes, you'll see this. It was just piecewise linear interpolation to show the policy, because you're right. It's only defined in integers. Yeah, it's crazy. All right, cool. So, and so there's 2 things you can do. Again, you can just say, I'm done, solve the problem, and now the stochastic model is good for validation and performance approximation, things like that. Or you can put this into something like reinforcement learning. And so you can use this structure, the fact that we have the structure to come up with a basis for reinforcement learning, and we will do that. That'll be a homework assignment later. Okay, so that's it, I think, right? Out of time? I think so. So next lecture, I'm going to give you an elegant, simple proof for the dynamic programming equations. I feel really bad about making a mess of it last lecture. It's really simple. It'll take us 5 minutes. And then I want to do the LP approach, to get that, that intuition in there. I'm not going to go through all the details, but I'll give you the main ideas, So this linear programming approach. And then, it's policy iteration and value iteration. That's the end of the full state optimal control, because after that you have to start thinking about partial information. All right. Any questions here? Thanks for the help. Yeah. So on to office hours now.